So, good evening, everyone. I am Rakhi Yadav, your PMRF teaching assistant for Pericyclic Reactions and Organic Photochemistry course, which is conducted by NPTEL and whose course instructor is Professor Sankara Raman from IIT Madras. So, students, in week 1, we are going to learn what is pericyclic chemistry, which type of reactions are we going to read in this course. So, before going ahead, you should know what is pericyclic means. What peri means around the circle, right? Or just we have read that perimeter. So, in this reaction has been characterized by cyclic transition state involving the pi bonds. Okay, bonds are made or broken in concerted way, not in like your cationic anionic mechanisms, right? They don't involve any intermediate. And most important point for pericyclic reaction is that reactions are completely stereospecific. Means the configuration of your product is totally dependent on configuration of your reactant and reaction conditions. So let's see first what are the types of pericyclic reactions. First one is your electrocyclic reaction, which we are going to cover in this week or today. Second is your cycloaddition. Third is your sigmatropic reactions. Fourth, kilotropic reaction. And fifth is your group transfer reaction. So, in this week, we are going to cover electrocyclic reaction, which are characterized by they are actually one component reaction, one component reaction, and when we let's say this system you are given and it is changing to on cyclization, you will get this cyclobutene, right? So in reactant, there are two pi bonds and one, two, three sigma bonds, correct? And in product, you are having one pi bond and four sigma bonds. From here, you can make conclusion that electrocyclic reactions are characterized by that one extra sigma bond is forming on the coast of one pi bond, right? So this is also a key feature of electrocyclic reactions. So students, in first 10 to 15 minutes we are going to revise concept which sir have already told you in this week 1 lectures. So first, in electrocyclic reaction you should know how to draw molecular orbitals for 4n system or n 4n plus 2 system. So first you should know how to categorize whether a system is 4n or 4n plus 2. So if you consider two main molecules such as first one is your what is this butadiene and this is your hexa 135 triene. Since this is having 4 pi electron, so it is 4n system and this is having 4n plus 2. Why? Because 6 pi electrons. So if you put n is equals to 1, it is 4n plus 2, right? So this is your 4n plus 2 system. Now according to frontier molecular orbital approach, there will be four wave function related to that, related to butadiene since it is having 4 electron. So let's draw from here. Psi 1, psi 2, psi 3, psi 4. Okay, wait. So if you draw all the molecular orbitals, you know very well that among these four orbitals, the main change is going to come in end orbitals, right? And you know the reason very well, because end orbitals are going to form a new bond, right? So what is the basic reaction of electrocyclic? That under electrocyclic ring closure, it is going to form this new sigma bond. So these two these two are known as end orbitals, right? So first you should know what are nodes. So node is a region where probability of finding electron density is zero, right? Formula for nodes is given by n minus 1. So according to this formula, in psi1 wave function, nodes will be 0. So if node is 0, it will be like this, right? All same phase orbitals are going to overlap. So no node. In psi 2, according to formula, how many nodes will come? 1. And you should locate that node perfectly symmetrical. So only one possible location where we can put this node is this. For that, they should be different orbitals. But here there should be no node, so same. And here positive, positive, correct? In psi 3 case, it will be like positive, negative, negative, positive. Why? Because there should be two nodes. One is here, one is here, and here since they are same phase sign, so there will be constructive overlap. In psi 4, nodes will be 3. So, 3 nodes are there. So, this is a way to draw molecular orbitals, right? Now you should know under there are two conditions possible. One is thermal, one is photochemical. Under thermal condition, since butadiene is having 4 pi electrons, correct? One, 2, 3, 4. Under thermal condition, for butadiene, side 2 is homo for butadiene, right? Your homework is you have to draw molecular orbital for this. Draw molecular orbital for hexatriene. Okay. So for butadiene, your psi 2 is homo and psi 3 is homo for photochemical condition. Because in photochemical, one of the electron will excite into psi 3. Correct? Now why I am telling you all this? Let me explain you. So in electrocyclic, your first target should be you should know whether your system is 4n or 4n plus 2. After you got to know that your system is 4n, let's say, then you have to find in which type of wave psi is your homo is there. For butadiene, psi 2 is your homo in presence of thermal condition, and in presence of light, psi 3 is homo, right? Let's say psi 2 is homo in thermal condition, and it is that since end orbitals are playing key role here, and you should know when psi is even, end orbital signs are different. When end orbitals sign are different. So in which rotation you should move these two orbitals so that their constructive overlap can take place. For that, you should move both the orbitals in same direction. Then only they can meet. How? On rotating this first one, it will change into this one, minus positive. And this will change into positive. So for constructive overlap, if your psi is even, you have to do cone rotation. And in similar ground on similar grounds, if psi 3 is your HOMO in case of photochemical condition, you have to do disrotation in order to have constructive overlap of your end orbitals to form this new sigma bond. Right? I hope I'm clear to you all. So you can see in this, in case of butadiene, there are four molecular orbitals, right? Since there are four pi electrons, 1, 2, 3, 4. In case of thermal condition, psi 2 is HOMO. In case of photochemical condition, psi 3 is your HOMO. Okay. In case of electrocyclic reaction, basically you should know what is your HOMO on basis of condition provided. For example, in case of ethylene, your psi 1 is HOMO, and in HMU condition, psi 2 will be your HOMO. So, what are pericyclic reaction? It is that type of pericyclic reaction where you just have to move pi bonds and form a ring. Or another possibility is also there. There are two possibilities. Either this bond is shifting there and this bond is coming there, and you will form this cyclobutene, right? This is your electrocyclic ring closing. And another different type of, whenever you see this type of system, right, it can undergo electrocyclic ring opening, and it will lead to formation of this. Both are electrocyclic reactions. So basically what I want to say in this slide is, electrocyclic ring can be, the ring can be opened and closed also. And we have also seen how we have also arrived to Woodward Hoffman rule. So we have seen in case of butadiene under thermal condition. See, there are two conditions possible: thermal, HMU, correct? And two type of system possible. System. Your system can be 4n type. Your system can be 4n plus 2 type, right? When your system is 4n, for example, in case of butadiene, under thermal condition, what was its HOMO? Psi 2. When psi 2 was HOMO, in that case, under thermal condition, psi 2 was HOMO, if you remember. And orbital sign was different, correct? To have constructive overlap, they should move in cone rotatory fashion. And in HMU case or light case, they should move in disrotatory, because for butadiene psi 3 was HOMO, correct? On similar grounds, when you draw for hexatriene, you will get to know that 4n plus 2 system under heating condition, uh, let me draw for you for hexatriene, right? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So under thermal condition, psi 3 is your HOMO for hexa 135 tri, right? And orbital sign would be same because it is psi odd. And for same sign orbitals, you have to give this rotation. So in HMU case, automatically it will be cone rotator. So till this slide, we have learned two new things. First, we have to determine whether our system is 4n or 4n plus 2. And second, We have to determine in thermal condition either it will be cone rotatory or disk rotatory, and in a photochemical condition either it will be cone rotatory or disk rotatory. Okay, so this is very good practice for you. You can pause the video and just tell me what type of system it is this. So see how in electrocyclic reaction it is not always necessary that it should be pi electron involved should be 4n, right? So 1 2 and wait. So in case number 1 there are 4n electrons involved, right? 2 sigma, 2 pi and 2 sigma. Here 4n plus 2, 6 electrons are involved. Here 1 2 3 4 5 6 7 8, 4n electrons are involved. Here again 4n, 1 2 3 4, they are in conjugation due to this positive charge. Here 1 2 3 4 5 6, therefore 4n plus 2. And in this case 2 of this sigma, so 4n plus 2. If you keep it n is equals to 0, it will become 4n plus 2. Here it will become 4n. Correct? It's your homework. You should know under thermal condition it will go under which type of rotation. I have discussed with you. You can see previous slides for that. So students, this is your problem number 1. You have to tell me product and you have to tell me orientation of these groups. Pause video, take 1 minute and try to solve this question. So your first target is you should know what type of system it is. This is foreign system, right? Condition is thermal. Now tell me, under foreign system, under thermal condition, will go which type of rotation? Mode of rotation. It is same like your butadiene, right? Foreign system. Under heating condition, what was its HOMO? Psi 2. And psi 2 end orbital sign was different. For having constructive overlap, they should go in cone rotatory fashion. Correct? So, one thing is clear that you have to open this ring. Whenever you see cyclobutene system and heating is there, think for this. Correct? Now your next target is to tell me among CO2, Me and H, which group will be where? Outward or inward? For sake of simplicity, just try to draw this way. Okay. See, you can visualize this in this way. You want both the CO2 Me group cis in your here. Here you want them cis. And you very well know that foreign system under thermal condition undergoes cone rotation. Correct? So positive, negative, negative, positive. So under cone rotation, there are two possible products. One is this and one is this. This is nothing but your CO2 Me group, correct? CO2 Me, CO2 Me. Let's say this CO2 Me I am referring is here as is equals to E. Okay. So among these two intermediate, or which can give me this cyclobutene in cis. Remember, you have to do cone rotation. So if you are doing cone rotation in this way, this CO2 Me will go up and this CO2 Me will go down. But in starting material, they are syn. So this should not be possible. But here, under this condition, this this CO2 Me group will go above and this will also go above under cone rotation, right? Above na? So therefore, it should be this. Or another possible is both are same product, but for your sake of understanding. So correct answer for this question is another way to understand is from here also. Yeah? Since these two bonds are, let me draw here. These two CO2 Me groups are above. Okay. And these, let me draw by rubbing this. It is not working actually. Yes, now it is working. So another way to understand this problem is you just draw. See, this is your present scenario, correct? In order to make these two lobes apart, then only this ring will open and will convert into this butadiene type of system, correct? And you know very well that foreign system under thermal condition goes cone rotation. So let's say you are rotating this below lobe like this. So you have to rotate this lobe also in same fashion, correct? And when you will do this, you will find that one CO2 Me will go upwards and another will go only in this direction, correct? Basically, in conclusion, if they are in same side of your, I will say cis in starting, so they will be on same side in product also. They can't be opposite. Both will go upward only. Correct? I hope I'm clear to all of you. So this is your problem number 2. You have to tell me intermediate involved in this reaction. Last step is nothing but your aerobic oxidation just to get aromaticity back. Take 1 minute, pause video, and think which pi electrons you can take for this reaction. First of all, you should know that only electrons possible are these 1, 2, 3. It means 6 pi electron 4n plus 2 system. 4n plus 2 system under H mu condition undergoes cone rotation. Correct? Till here. Clear? Now you just have to shuffle these pi bonds. And you what type of intermediate? Just draw other things similar. This one. And you will get this type of intermediate. And this is your answer. But in order to get aromaticity back, they are doing this aerobic oxidation. So now you have to tell me these hydrogens are there. Either they will be cis or trans. Tell me. So let me tell you. This is your system, right? So if you are looking at your system, you can see that these hydrogens are opposite, right? This is going that side and this is going this side. Not they are going similar side, correct? And under cone rotation, they will be trans only, as I have told you earlier. If they are facing same side, they will be same in your product. If they are facing different side, for example, in this case, you can take example of this. Most easy example to understand. If they are like this way, they are opposite. If they are like this way, they are same. Okay? So here in this case, they are opposite. Or another best thing to learn is if your reacting olefins are EE or ZZ, they are opposite. And if your reacting olefins are EZ, they are same facing substituent. Okay. So just you should know in cone rotation. In cone rotation, if they are opposite, in product also they will be opposite. And in this rotation, if in starting the substituents are opposite, in product they will be same. Okay. So you have to follow this rule. First you should know what type of system 4n or 4n plus 2. After that you should know under given condition whether it will go this rotation mode or cone rotation. Okay. Then you should know direction of substituent, which is main thing here, right? If you are not able to find direction, you can use this strategy. If olefins are EE or ZZ, they will be opposite. If olefins are EZ, they will be same. I can again explain you. For example, like this. Let's say this is your OMe, this is your chlorine. This alkene is E alkene, right? E alkene, and this is your E alkene. So it means direction of substituent is opposite, and we can see also, but in every cases it is not possible to imagine the direction of substituent when it come to complex problem, right? So in these type of cases, we just have to remember that if the olefins are EE or ZZ, they will be opposite. If one of the olefin is E, for example here, if if one of the olefin is your E and another is your Z, this is E olefin, this is Z olefin. Since direction of substituents are same, so they will be considered as same. And if this type of system is undergoing cone rotation, since the substituents are in same direction, in product also they will be in same direction, or they will be cis. I hope I am clear to everyone. So it's time to go to problem number 3. So in problem number 3, students, you have to tell me which electrons are undergoing electrocyclic reaction. First question. Second is, what is the stereochemistry of the product? Since now I have told you how to do in electrocyclic reaction now. Only these three things are there. Your mind should read which electrons are going to take part in reaction. Second, which type of rotation it will undergo. And third, stereochemistry of the product. And your job is done. Take 1 minute for this question and then we will start discussing. If you, if you look at the product, it is simple question that cyclobutene is forming. It means somewhere in your starting material, butadiene type of system is there, correct? And you can easily see this. This will go there and that will come here. And just give numbering 1, 2, 3, 4, 5, right? It will form this four membered ring. Now you have to tell me OMe and H stereo. That and another is 1, 2, sorry, 1, 2, 3, 4, 5. So this five member ring is as it is, right? Now you just have to tell me, just forget about this right part, that is intact. Otherwise this system is like this, your simple butadiene system. OMe, hydrogen is going there, correct? This is your this system is almost equal to this. Here your OMe and H are opposite, correct? One is going upward, another is going. I am looking at direction of substituents. Or more easily you can understand in this way, correct? This is your OMe, this is your H. Now you have to tell me 4 n electrons are there, okay? Under H mu condition, what will be their HOMO? 4 n H mu, what will be their HOMO? Psi 3, correct? If psi 3 is HOMO and orbital sign same, it will undergo disrotation, right? On this rotation, the things which are on opposite side, they will become sin, or not sin, cis, right? So this is your final product. or uns. I hope you are clear. If you are not, let me tell you. End orbital sign should be like this. Psi 3 will be homo, right? So, in order to have constructive overlap, one bond should go there and another should go there. So, OMe and H will come on same side, right? Therefore, stereo of the product is cis. I hope it is clear to everyone. This is very good problem for you. Just take a pause and try to solve this question. One big hint is if you anywhere see cyclobutane, since it is very strained system, right? Because ideal angle of cyclobutane is 90 degree, your square, right? Here double bond is also there. You are deviating it from 120 degree to 90 degree. So this type of system under heating or thermal condition, under thermal or photochemical condition, they will try to open as fast as possible. Correct. So let me start solving for you. This is your pH. This is your pH. Double bond O, pH, pH. Correct? So first it will undergo electrocyclic ring opening. How I am telling? Because cyclobutane is there, hitting there. Only condition is this. And another kick in this question is that you have to just open one of the phenyl ring. Now, can anyone tell me what, how many electrons can be involved here? Since you can see in product also, we just have to suggest a mechanism by looking at product. But another thing also, there are 6 electrons you can see which are in conjugation. 1, 2, 3, 4, 5, 6. Correct? So this can undergo. This is 4 pi ERO and this is 6 pi electrocyclic ring closing. Correct? So this bond can go here and this can go here. And what you will get, let me draw here, pH, double bond O here. Here you will get pH, one double bond between them, and this pH, double bond one come here, and another is, and last step is nothing but your tautomerism. Tautomerism will take place in order to attain aromaticity. Correct? So when you are solving this, don't look at solution and try to find out what changes have been done and how I am approaching this question. Since 4 pi electrons are involved, okay, not 4 pi but 4 electrons are involved, heating condition is there. 4 electrons under heating condition will undergo 4n heating, psi 2 homo, and orbitals different means cone rotation, right? Cone rotation, if they are going, they will form this ketene intermediate. Uh, we call this we call this type of system as ketene, right, students? And then we can look at it in this way that 6 pi electrons are there. They will undergo ring closing. and will lead to formation of this upon tautomeres. So this was good question. You should know how to approach these type of questions. So now it's time to solve problem number 5. How you are going to start solving these type of problems. First, let me tell you what you have to tell me in this question. In question mark, you have to tell me either it is heating condition or thermal condition. Sorry, either it is thermal condition or photochemical condition. In these type of questions, you can't solve from starting. You have to see what is there in product, then you have to tell me. So one thing is clear that this new bond has been formed. If you draw its retrosynthesis, I hope you all know retrosynthesis, or you should I can use a simple term. If you can go backward, this type of system should be there, right? Or just do this way, if I am not wrong. Yes, na? Yes. Now draw this thing similar. Correct. Now you just have to tell me whether these hydrogen will be syn or what. See, let's calculate how much number. One, 2, 3, 4, 5, 6, 7, 8. This is 8 member ring, correct? 8 member ring most stable conformation is there. This is on this only, right? So if you draw in this way, correct? This is your, is something wrong here? Oh no, good. So this is your Me. So one thing is clear that your A is this. And another thing is, you know A. Here hydrogen are opposite. How I have told this last. See, let me use another color to explain you. Since your reacting partners are this, so you have to just look at configuration of these two olefins. This is your Z olefin. This is also your Z olefin. Correct? I have told you in earlier slides, if reacting olefins means last olefins are E or ZZ, means direction of substituent is opposite. And if they are EZ means C. And by looking at structure also you can know that they are opposite, correct? One is going that side. So, but in here they are syn, but here they are opposite. So one thing is clear, here you have to do which type of rotation? Obviously disrotation. Disrotation is required. Now students, you have to see how many electrons are involved. 1, 2, 3, 4, 5, 6. Means 4n plus 2 system. 4n plus 2 system under which condition will undergo disrotation? Tell me. Heating? Correct. Why? Let's say example of hexa 135 triene. Psi 3 will be homo. Psi 3 means end orbital sign are going to be same, and for their constructive overlap you have to do this rotation. So one thing is clear, here condition will be thermal. Photo, oh sorry, heating. So your A is this, condition is your thermal. Now how will you form this A from this? This is too very easy. You have to do this. Just rotate these bonds. Now you can see direction of substituent of methyl is same. By looking at also you can say that in reactant your methyls are at same side. Correct? But in product if you see they are trans to each other. Yes or no? So in starting they are same. In product they are trans. If you are doing cone rotation, same will remain same. But you want but you want them in trans. So one thing is clear, you want this rotation here. How many electrons are involved? 1, 2, 3, 4, 5, 6, 7, 8. 4n system under which condition will undergo this rotation? Obviously H mu condition. So first condition will be your H mu. So this is the way to solve these type of problems. Take 1 minute to get feel of this and then I can explain again also. I hope I'm clear to everyone. If not, listen video again. You will get. It is very easy. You just have to go stepwise. You should know the basic concepts. You have to see that stereochemistry is going to remain same. Under cone rotation, same side substituent will be are going to remain same. Under this rotation, if they are in same side in starting, they will be at trans in product. Okay. So now it's time to come to problem number 6. Let me read for you. Which of compounds among A to D is the likely intermediate of the following transformation involving two electrocyclic reactions, ring opening and ring closure? They are asking that in order to get this product P from reactant R under heating condition, which intermediate is going to form? First, I have told you, whenever you see this cyclobutene, just open it, correct? So after this 4n system under heating condition will undergo cone rotation, right? Because psi 2 is home. If it undergoes cone rotation, it will form this. This is connected here, right? So this intermediate is there in B option. So option B is correct. Now you may think that here why other options are not correct, because see here outside there are three pi bonds, but let's say here, but if you go stepwise, obviously this bond will be here, but here no pi bond, so it is cancelled. Again this also, and at last what will happen? This will go there, and Again aromaticity will be back and you will get product B. I hope I am clear. Yes or no? In electrocyclic, wherever you see strained systems such as cyclobutene, it will try to open up. You have to see number of electron involved. Then you have to see condition, either it is thermal or photochemical. Then you have to find out mode of rotation. And for finding stereochemistry or direction of substituents in product, you should know what is the direction of substituents in your starting material. Correct? And if in starting material your direction of substituents are sin, not sin, they are going towards same side. And under cone rotation, they will be cis-on. Because pericyclic reactions are highly stereospecific. Stereochemistry of product is totally dependent on stereochemistry of reactant. In problem number 7, they are asking which of the following is classified as an electrocyclic reaction. See, in slide number 2 or 3, I have told you that electrocyclic key feature of electrocyclic reaction is what? If you look at this, you can see that there are two pi bonds here, one pi bond. Three sigma bonds here, four sigma. Means in electrocyclic reaction, one pi bond is less in product. But here, two pi bonds in reactant, two pi bonds in product. So A option is deleted. Here, two pi bonds in product, one is in reactant. So yeah, this can be electrocyclic reaction. Third one is your actually in reaction, which you will study later. Correct? And fourth one is your simple carbene insertion. So this can't be electrocyclic. So most appropriate answer is B. How I solved this question? By looking at key feature of this electrocyclic reaction. In problem number 8, they are asking the following reaction involves a take 1 minute time and start solving this question. So basically, there is one problem in this product. I have solved this earlier and found out that, but before solving or looking at solution to this problem, you should figure out what is the problem in this product. Okay? Okay. Let's move ahead. See, one thing is clear that this bond is forming. So obviously this will go here, this will go here. Everything is in conjugation, right? If we look at this, what will form? Just draw carefully. This bond has come here. This has gone to wait. right? This bond will shift here, this will shift here, correct? And we are left with these substituents N, pH, Me, and this hydrogen. So what was wrong in this product, that they have made it a completely aromatic system. But in our main motto should be, we should know what will be the stereochemistry of this NPH, Me, and H, right? Since they have given they are trans, so we have to figure out condition under which condition they can be trans. Okay. First, if we look at option number 1, they are saying at photochemical 10 pi electrocyclic ring closure. Okay, 10 pi, let's see, 1, 2, 3, 4, 5. Yes, 5 bonds, 10 pi electron, good. Ring closure, good. But 10 pi electron are your 4n plus 2 system, correct? Under photochemical condition, it will undergo cone rotation. Good. Cone rotation, NPHMe is here and hydrogen is also here. In other words, they are same. Correct? They are same. NPHMe is coming downward. This your hydrogen is also coming downward. So if cone rotation is there, they will be syn, but they will be cis, but they are trans. So option number 1 can't be true. We can easily delete option number 2 and option number 4 because no 6 pi electrons. There are 10 pi electrons involved in this reaction. Okay. So only correct option is this, and it obviously this will be correct because 4n plus 2 system under thermal condition, it will be what? 4n plus 2 system under thermal condition will be disrotation. Why? You can see in any type, in any number of electrons is given, let's say 18 electrons are there, you should not memorize all things. For foreign electron system, you should keep reference your butadiene. For foreign plus 2 system, you can keep your references hexa 135 triene. You know that if 10 pi electrons or 4n plus 2 electrons are there under heating condition, they will undergo disrotation. Okay. Why? Because in hexa 135 triene, side 3 will be your HOMO, correct? And for constructive overlap, they should undergo disrotation. And disrotation can only give you these two substituents in transposition, correct? I hope I am clear to everyone. So this is your problem number 9. Explain why the orientation of hydrogen differs in the product of electrocyclic ring reaction. Very good question. If you have understood till this part of this session, you will be easily able to solve this question. You just have to tell me why they are cis in first, why they are trans in second. Okay, let's start solving this question. So, students, first you should know what type of system it is. Okay, so it is clearly visible that it is 6 pi electron system, means it is 4n plus 2. 4n plus 2 under heating condition will go under disrotation. It is very clear. Good. See, if direction of substituent is cis in starting material, on disrotation in it will change to trans. This thing should be clear. So if we want this 4n plus 2 system in heating condition is disrotatory. So if we want things in cis condition, And one thing is obvious, it will be disrotatory only. So if you see here, hydrogen is here and here hydrogen is here. So it is obvious that we can consider it is like that. These two hydrogens are opposite. On this rotation, they will go same side, above, above. Okay, it will form this na hydrogen above, above. So yeah, correct. And if we look at here, this hydrogen is going above. This is also going in same direction. So obviously on this rotation, they will go trans. So this was the reason why the orientation of hydrogens was different in the product of electrocyclic ring closure. Last question for today's practice session is determine the manner in which ring is closed for the given electrocyclic reaction. Very easy question this. See, this is obvious that this is electrocyclic ring closing. With which type of system? 4n plus 2. Condition, heating, closure, cone rotation or disrotation. Students, 4n plus 2 under heating condition, psi 3, remember? So it will be disrotation. Good. This is E alkene, this is your Z, means direction of substituent is same. Therefore, they will be trans in your product. So this is answer for this problem. I hope everyone got this. So from this practice session or week 1 tutorial, what we have learned is pericyclic reactions are divided into various parts. In this session, we have covered problems based on electrocyclic reactions. Electrocyclic reaction can be of two types. Either they can be electrocyclic ring opening or electrocyclic ring closing. Okay. After that, you should know what type of system it is. Either it is 4n system or 4n plus 2 system. Okay. Then you should know what condition is giving, heating or thermal. Then you should know which type, uh, how we have arrived to Woodward-Hoffmann rule. That 4n system under conrotation will undergo which 4n system and in presence of thermal condition will undergo cone rotation, right? And for cone rotation, what you have to do? Psi 2 is your HOMO, therefore it is going cone rotation. I again explain to you. If this number is even, right? Even and or and orbital sign will be and orbital sign. Different, and if they are odd. For this type of system for constructive overlap, it should have to go under cone rotation. And for this type of system to have constructive overlap, they should undergo disrotation. Okay. So this was the take home message from today's session. Thank you everyone for listening me. If you have any doubts, you can tell me in next practice session. Thank you for joining the class. I am ending call here. Okay. Thank you.